All right, the next concept on periodicity we're going to cover, or atomic structure, is trends. So when we go and we have our periodic table, when we go across the period, or we go down a group on the periodic table, what are the trends when it comes to some of the properties of these elements? And this again is pretty much all review from honors chemistry. And the trends you need to know about are atomic radius, the overall size of the atom, the ionization energy, which is the energy needed to remove the outermost electron, the valence electron farthest from the nucleus in the outermost orbital, how much energy it takes to remove it, and electronegativity, which is the ability of an element to attract an electron in a chemical bond. Not only to know what they are, but more importantly, probably on the national exam, would be to predict what would happen or explain why this element has this value and this element has this value. To explain it, we have to utilize Coulombic attraction. And again, if you remember, that is the attraction, the force of attraction between the nucleus and the valence electrons. So let's say this element has got electrons on the second energy level. So we're looking at that attraction of that nucleus to that outermost electron, how much attraction there is. Now, there are three variables that affects the amount of attraction of the valence electron to the nucleus. The first is distance. How close is the electron to the nucleus? Now, when we go across the period, the electrons are being placed in the same energy level. Therefore, the distance variable really is not changing much. The distance variable changes when we go from an energy level further and further away from the nucleus. So when I'm going down a group, my valence electron is in an energy level farther and farther from the nucleus. That's when the distance variable is changing. Now, as the distance variable increases, what do you think happens to Coulombic attraction? What happens to the attraction of the electron to the nucleus? Okay, the Coulombic attraction decreases. So when we go down a group, the primary thing you want to talk about, if they ask you to justify, the primary thing that happens is that the Coulombic attraction decreases because the valence electrons are located in an energy level farther and farther from the nucleus. When we go across the period, it's the other two variables that we want to talk about. The next variable when we go across is the nuclear charge. The charge on the nucleus. When I go across the period, the electrons are being placed on the same energy level, but I'm also adding more and more protons to the nucleus. And if the nucleus has got more protons in it, it's got a greater nuclear charge. Since the distance variable is not changing very much, and the nucleus is gaining a more positive charge, there will be an increase in Coulombic attraction if the nucleus has got more and more protons in it. So when you go across the period, that's what you want to talk about. The nucleus has got more protons in it. It has a greater charge on the nucleus, and that causes a greater Coulombic attraction to the valence electrons. The distance variable really is not changing much, and therefore it's the nuclear charge that explains the period trends. So you go across, talk about nuclear charge. When you go down, talk about group. There's a third variable that affects Coulombic attraction, which I didn't talk much about in honors, and that is called the shielding effect. When we go down a group, there are more and more electrons in between the valence electrons and the nucleus. And we call those in-between electrons the inner shell electrons. Well, the inner shell electrons, they repel the valence electrons. And that repulsion actually minimizes or lowers the nuclear charge effect, because that repulsion cancels out the attraction to the nucleus somewhat. So the shielding effect, as we have more and more inner shell electrons, when I go down a group, if there's more electrons between the nucleus and the valence electrons, which happens when I go down a group. When I go across the group, it doesn't. When I go across the group, I'm not adding any more inner shell electrons. I'm adding electrons to the valence shell. Excuse me. So when I go across the period, the shielding effect does not change, much like the distance. The only variable that is changing significantly is the nuclear charge. When I go down a group, now, even though the nucleus has got more and more protons in it, the distance variable and the shielding effect, those two variables overweigh and outtake the increased size of the nucleus. Okay, so as we have an increased shielding effect, that decreases coulombic attraction. Okay, so to just pretty much summate these findings, what happens to coulombic attraction when we move across the period? We move across the period, coulombic attraction decreases. Why? Oh, excuse me. Totally my fault. When I go across the period, the coulombic attraction increases. Why? The distance variable is not changing significantly, but the nucleus has got a greater charge. And this causes a greater coulombic attraction of the valence electrons to the nucleus. When I go down a group, coulombic attraction decreases, mainly because of the distance variable. The distance is increasing, so the valence electrons are in orbitals, I shouldn't say orbitals, energy levels, use the word energy levels farther from the nucleus. And this distance variable is greater at affecting coulombic attraction than the actual nuclear charge. And by increasing the distance, now there is a lower coulombic attraction because the two particles are getting farther and farther away from each other. All right? This right here, coulombic attraction, is the justification used to explain all the trends on the periodic table. So the atomic radius, the sizes of atoms. When we go across the period, because coulombic attraction increases, the sizes of atoms get smaller. When I go across the period, the atoms are getting smaller and smaller and smaller. So when I go from the periodic table, the row of, let's say, I'm trying to think of one off the top of my head, the one that I know of, like the second row, where I happen to have lithium to neon, as I go across that period, lithium is the biggest atom in that row, in that period. Neon is the smallest. You'd think that it would be getting bigger because it's gaining more subatomic particles, but it's actually getting smaller because the electrons are being placed in the same valence or energy level, but the nucleus is getting a greater and greater charge to it, and that pulls the electrons into and makes it a smaller size. When I go down a group, coulombic attraction weakens and the sizes increase. So when I go down a family, they get bigger and bigger because the valence electrons are in higher energy levels, and that decreases coulombic attraction. Okay? Ionization energy is the amount of energy it takes to remove an electron. If the coulombic attraction is weaker, there will be lower ionization energies. And the first ionization energy is the amount of energy it takes to remove the first electron from an atom. So the atom is going to become a +1 cation. Okay? So if the coulombic attraction is weaker, the valence electron is less tightly bound to the nucleus, therefore it'll take less energy to ionize it. Therefore it'll be easier to ionize. So as we go across the period, coulombic attraction increases, and therefore the ionization energy values will get larger and larger. Because there's a greater coulombic attraction, it'll take more energy. So it takes more energy to ionize neon than it does lithium. Okay? So ionization energies increase across the periodic table. When I go down a group, the coulombic attraction weakens and the ionization energy values get smaller and smaller. So when I go down a family, elements further down the family or group have lower ionization energy. It takes less energy to ionize rubidium than it does lithium. And that's because the valence electrons are farther from the nucleus. It is easier to ionize and remove those electrons. Lastly, electronegativity. Again, electronegativity is directly related to coulombic attraction. If there's a greater nuclear charge effect, a nuclear charge pull, they will more likely gain or want to gain electrons, or there's a greater affinity or a pull to gain more electrons. So again, when I go across, Coulombic attraction increases, and therefore electronegativity values increase as well. When we go down, Coulombic attraction values decrease, and electronegativity values also decrease. And if they're asked to justify, the nice thing about all three of these, it's the same justification. When you go across, the nuclear charge is greater, while the distance variable isn't changing much. Okay? When you go down, the distance variable is changing, and because the electrons are farther from the nucleus, even though the nucleus has a greater charge on it, the distance variable is the outweighing factor. Also increased shielding effect, you can talk about briefly. Talk more so about the distance, and that's causing the Coulombic attraction to be weaker. Okay? One thing to note about electronegativity is we have to exclude the noble gases. The noble gases tend to have electronegativity values of 0, and that's because they have a full valence shell already. So even though they do have the greatest Coulombic attraction, so their outermost electrons, this trend doesn't hold true for the noble gases because they do not want to gain any more electrons because of their stability in having a full shell of electrons in all their shells. So that's one thing that's a little bit different with electronegativity. It's typically why most questions on the national exam tend to focus just on A and B. But do be prepared in case you would happen to have C. We should know that fluorine is the most electronegative atom, and therefore it is the element that gains electrons the most, and that's why it has an oxidation number always of -1. It always wants to gain one electron. It is the most, or is the best at gaining or pulling electrons towards it because of its high Coulombic attraction. All right, a couple of things, just tidbits to talk about. Ionic radius is looking at what happens to the size of an atom when it goes from an atom to an ion. If it becomes an anion, a negative ion, it has gained electrons. If you've gained electrons, you've increased repulsion. What do you think that does to the size? It increases the size. So if I have the sulfur atom and the sulfide ion, who's bigger? The ion is bigger because it's gained electrons. That extra repulsion in the valence shell will cause it to swell. We haven't gained any more protons. There's no more nuclear charge. So anions are always bigger than their atoms. Vice versa. If I take a sodium atom and it now becomes a cation, a positive ion. We've lost electrons. Where do we lose electrons from first? The valence electrons. And if I lose the valence electrons, the atom is going to get significantly smaller. So atoms are always bigger than their cations. One extra additional trend to that is what happens if you have an ion like the D block that have multiple possible oxidation states. Well, as I keep losing more and more electrons, it keeps getting smaller and smaller because the remaining electrons have got a lower shielding effect and a greater nuclear charge over the other elements, and that reduced repulsion, because there's less electrons there, will cause it to become smaller and smaller. Okay? Lastly, isoelectronic series. Iso means same or similar. An isoelectronic series are particles, either ions or atoms, that all contain the same number of total electrons. Argon, chloride, -1, calcium +2, and titanium +4. All of these particles have the same number of electrons. They all have, I believe, 18 electrons. Are they the same size? What do you think? The answer is no. Why? What's different about them? They all have a different nuclear charge. They all have a different size of nucleus, and that's going to cause a different pull over the same number of electrons. If there's a greater nuclear charge, the size of that particle will be smaller. So we look up, for all of these, we look up their number of protons. Argon has 18 protons, chloride has got 17, calcium's got 20, and titanium's got 22. Therefore, the one with the most amount of protons is not bigger. That's a misconception. It's remember the nucleus is usually about 10,000 times smaller than the electron cloud. So, even though there's more protons, the nucleus is tiny compared to the electron cloud. More protons or greater nuclear charge is going to make the same number of electrons be pulled into the nucleus more tightly. Therefore, chloride is going to be the largest. Oops, and it says order of increasing size. My fault. So the smallest will be the one with the most protons. So titanium would be the smallest, then would come calcium, then would come argon, and then would come chloride. That would be the order of going from the smallest to the largest. So if you have an isoelectronic series, always figure out how many protons and how many electrons you have. And then if you're talking about size, if they have the same number of electrons, then you look at the protons. What is the variable? What is the independent variable that is changing and causing the effect? What's the independent variable causing the change in size, which is in this case the dependent variable? Okay, so these are all things we talked about in honors chemistry. Please review them. I'm going to post today on Canvas a short homework on some questions when it comes to sizes of elements, and some questions and even some past questions on the national exam, and give that homework a try. On the next page, I think I stopped myself from talking here. So again, use this page, read it through, and when you read it through, it kind of talks about exactly what I talked about on the previous page. But it's a nice place just to kind of, if you need to always come back to it, and versus having to listen to me for 15 minutes, you can just read through these trends or have these out and available to you. But again, try to wean yourself from them when you answer questions so you get that down into your memory. But review these concepts. The equation for Coulomb's law is up above, and you can see here why the distance variable will often trump the nuclear charge variable. And that is because there's the distance has a square on it versus nuclear charge does not. So these are different things to read through and consider when you're looking at properties of Coulombic attraction, how that affects the three main properties that you should need to know coming into the national exam. I will post a homework set on Canvas today. Please try those problems. It should be a fairly short homework set. I'll place the answer key as always on there. If you have any questions, shoot me an email or a notification on Canvas. I'll be great to answer your questions. Keep on doing a little bit every day. Keep studying. There's less material to have to know for this exam, and it's critical that you keep reviewing and prepping yourself and not just decide to cram a day or two before the test. Use the time you have now at home to do a problem or two a day. Whittle out 20 minutes a day. Try to do some AP chemistry, and you'll be better off it in the long run. Okay? If you have any problems, let me know. Otherwise, hopefully everything at home is well, and hopefully we'll get over this in the next couple weeks, and maybe we'll meet again. Okay? Have a great day.